Hi everyone. Today I'm going to give a presentation on my final term project for EE275, which is Advanced Computer Architecture. I've taken this course at San Jose State University under Professor Chang Chu. So the project is a 5-stage Nios II processor implementation. This is implemented in Verilog HDL code. So the overview for today is the introduction, the hardware, how the hardware is designed, what's the architecture behind it, the simulation and the waveforms, and our conclusion. So coming to the introduction, so Nios II is a RISC architecture, which is a 32-bit processor. Basically it has various register sets which are 32-bit in size. So the processor is pipelined to 5 stages, so that each stage executes in parallel, and for every cycle you can execute each instruction. So the different kinds of instructions that are in the benchmark programs today are a load, store, add, and multiply, branch. So it took one cycle for all the instructions and 2 cycles for load and store kind of instructions. So this is the block diagram which represents my Verilog code. So first module is the fetch, then the decode, then it goes to an execute stage, and the memory access, then a write back. So this is pipelined in the middle. So the detailed block diagram is shown below. So this is my pipelined register set for fetch and decode blocks, and this is pipelined for decode and the execute, and this is for execute as well as memory and memory to write back. So you can see what I have in my fetch blocks. There is an instruction memory where I fetch my instruction set. My program counter fetches my instruction set, and it gets increased by 4. As I said, each instruction is 32-bit, which is 4 bytes. So it increments by 4 immediately, and the next program counter is ready to execute the next instruction in the instruction memory. So when it crosses the pipeline state, when it crosses the pipeline of fetch and decode, it decodes our instruction set, which is the 32-bit long binary code. So based on the binary code, it selects the register, source register, destination register, as well as the target registers, and the extension of the immediate values through the sign extension. So it is extended through this. While this is happening, the next instruction is read from the instruction memory. So the fetch cycle of the next instruction is done, and by the time the first instruction goes to the execute stage, our decode stage has its second instruction being decoded. So this is how a pipeline works. You can see here in detail. I can so these are the registers. So 31 down to 27 is one register, which is you can consider it as source. 26 to 22, it's the target register, and this is the destination register, and this is the memory write back register, which comes from the write back stage pipeline. So the 16-bit immediate value in the I-type instructions. So we have 3 kinds of instruction sets: I-type, J-type, and R-type. So I-type has an immediate value, 16-bit immediate value. So these values are converted to sign extended to 32-bit values, so that we can use them in the execute stage to perform the arithmetic operations on the sign extended value, immediate value. This ALU as well as this multiplexer tells us whether there is a branch instruction that has to be executed. So based on that, it goes back, and based on the mux, if the branch is equal to 0 or not, this mux selects the branch to be taken, or whether to take the next instruction in sequence, and that updates our program counter. So this is used for um, branch operations. And now here, based on the control signals, our mux in the execute stage selects the one of its input as a sign extended immediate value, or another register from the decode stage based on the I type or R type instruction. So if it is an I type instruction, we get the sign extended value from the mux, or if it is an R type instruction, this mux selects the second source register with the help of these control signals, and the ALU operation is performed. And now this the result is sent to the data memory, where it is stored in the data memory. So if we have a load word, so particular location is fetched, and that word, that data is sent to this mux. Or if we have an what do you call it, data that has to be stored back into the main memory, so based on this register set, control signals, this mux selects the data from the data memory to either to a load instruction, or to send back the calculated arithmetic result to the write back stage and store it in the main memory. So in fetch block, so as I said, we have a clock and reset. Based on the control signal, we select the next instruction in the instruction set, or if there is a branch, based on the control signal, we select the branched instruction to be taken. Whereas in decode block, so based on the PC input and the data, we decode the binary instruction format into a source register and an immediate value, or another target register if it is an R-type instruction, and particular outputs are sent to the next stage, which is an execute stage, the pipeline, which is a pipeline to the execute stage. So from the pipeline, we get the immediate data, source register 1 and source register 2 if it's an R-type, and our destination register. So again, with the help of our control signals, we select either the immediate data for an I-type instruction, or the source second register for a R-type instruction, and a respective arithmetic operation is performed and is sent out to the next pipeline, which is between the execute stage and the memory stage. So here we are in the memory stage. So once again, based on the control signals, the ALU in, which is calculated from the arithmetic unit, or what do you say, or the load data that has to be searched from the memory and sent to the register set to the decode stage to put it in a destination register. So the C3 selects which input, which data to be taken, and this is sent to the next pipeline stage, which is the write back stage. So in the write back stage, based on the control input, we select our data, either it's from the memory or from the calculated arithmetic unit, and we send it out to the write back loop. So you can see that in the here it's a write back data that goes back and stores in the memory. So I have run a 3 instruction set as assigned for the project. So first instruction set would be my this is kind of a benchmark program. First instruction set would be a dot product. So we have 2 vectors for this instruction set. I have given the data to be my student ID. So it goes this way. So this is my input. So the second input is twice of this input, so which are 9 in total. So the dot product for these 2 vectors, so this is an A vector A and this is a B vector. So the dot product is calculated with the help of the processor design, and our total is 128. The second benchmark program for this processor is factorial. So as in factorial, we initialize your register 1 to 1. So we check the condition if it is equal to 0 or not equal to 0. Then based on that, we go to our loops. Which is so if it's uh, 1, you just assign the result 1 and print out the output as 1. If the n factorial to be determined is more than 1, so we go to continue, and then from here we save our we increase our stack by using the push and pop operations, and then we multiply the n value that is decremented and saved over the stack. We multiply each of the n value, and finally we return it out through our stack pointer. And the third instruction set is the scalar addition. So it is like the address starts at 5000, our data address starts at 5000, where our data is stored, and it decrements down to 100 locations. It decrements down to 100 locations, and adds the data, which it's like basically it accumulates whatever the data it finds in the data memory and adds it up, sums it up. Yeah, so this is the dot product simulated waveform. So this is my first vector, this is the second vector. While calculating dot product, you can see with respect to the cycles how the Nios II processor that we designed have calculated the dot product. So finally we reach at 128, which is the result of our given vectors. And this is the factorial simulated waveform. So here you can see our given n is 4, so it decremented, so you can see the decrementation. And here the factorial result for each loop it iterated is shown here. So 1 times 1, and then 2 times 1, and then 3 times 2, it becomes 6, and 6 times the 4, it becomes 24. So yeah, 24 is the last, 4 is the maximum n that we have given, so it ended up at 24. And this is the scalar sum. So this is our scalar data scattered in the memory, and our processor have gone through the memory and added accumulated the data whatever it finds through the continuous 100 locations. So 1 plus 1 is 2, 2 plus 3 is 5. 2 plus 1 is 5. 2 plus 1 is 3, 3 and a 5, it becomes 8, 8 and a 6, it becomes a 14, and the rest of the data is 0, so it stays 14. So it accumulated the data it found in the memory from 5000 location. For this work, we can improve the design by implementing data forwarding as well as bypassing. So data forwarding is like if there is a dependency. So you have a register dependency here, so this has to be written back in register 2, and in the next stage it is being utilized to calculate and put the result in register 12. So if this is register 2 that is being calculated, so it is not available until the write back stage, but we need the register 2 here, so we forward our register data or bypass the register data to the next, so that so that the next instruction gets the updated value of the register 2. So this is data forwarding or data bypassing. So this project has a future scope of implementing this data forwarding and bypassing onto the existing code. That's it. So this is the end of the presentation. Thank you.